So far, just a little recap on where we're at with levers, because I've thrown quite a bit of information at you. And I just wanted to take some time to review the different types of classes of levers that we have, or the different types of levers. And so they're broken down into three categories: first class, second class, and third class. And how they're put into each category depends on the location of your fulcrum, or where it pivots around, and then where your effort force and your load force are. So first class levers, and probably the most common example you guys maybe will be able to relate to is, so an example is a seesaw. Remember those on the playground. So each of these examples uses some sort of load force, and then to show how you might move it, so we call that the effort force. So anytime we have to put effort into moving something, we call that the effort force. And the load, naturally with its mass and the effect of gravity, has a certain weight to it. So start to look at levers and try to think of identifying where the effort force is and where the load force is. So in this case, a load is on this side, and because of its weight alone, we call that the load force. And you're going to start to see some of these. So load force, we put force with a uppercase L. Effort, on the other hand, is our effort to move this load, because that's what the levers and simple machines are doing. They're trying to help make something that we're doing a little easier. So our effort force, it can basically go up or down. We have the ability to put some effort into rotating this lever amongst this pivot point, or fulcrum, which we call it. And so we call the effort force a capital F with an E. And it's the location of these three things that determine what class of lever you have. So if the fulcrum is between the two forces, then it's always going to be a first class lever. And an example you guys might be able to relate to is the seesaw. What I just want you to try to do as I work through these examples is try to think, okay, where would I label my effort force, and where would I label my load force? And usually the fulcrum will be labeled for you. So first class levers, you have your fulcrum between both of your forces. The next type is second class. Your fulcrum's at one end, your load is in between, and your effort to move it is over at the opposite end. So your most common example of this would be something like a wheelbarrow. So picture this: the wheel is where the actual canister or the bowl of your wheelbarrow pivots amongst, and you usually lift up this end to be able to move the wheelbarrow forward. So if you think about, the load always is the weight of our object we're trying to move, and it always pushes down because of gravity. So our load force is in the middle here. Fulcrum's at one end. At the opposite end, we have our effort force. And so this is usually us, at least in the case of a wheelbarrow, lifting it up with our effort. Okay, so those three things. And so second class lever, we have our effort force followed by our load, then the lever or the fulcrum last. And the final class is a third class lever. And again, we have our fulcrum at one end, except our effort and our load have changed positions. So our load, remember, is always the weight of the object, and because gravity pulls it down, our load force is always in the down position. And our effort, usually in this case, is us lifting the load at this end, and I'll give you an example of this that will make sense. So our effort force, most likely, if we're going to use this example, picture raising, let's say, a dumbbell. Ran out of board here. A dumbbell with your forearm. So your pivot point is your elbow. So if you picture this being your arm, your fulcrum is your elbow, and you're holding a dumbbell in your hand, so that becomes the load or the weight of the force, and you use your muscles to lift that load up. So it would be the muscles in your forearm to lift that load up, or the bicep, or the dumbbell up. Okay, so that's an example of a third class. So second and third class both have their fulcrum at one end. It's just the order of the effort and the load. The load's at the end for a third class, the load's in the middle for a second 3 things you should be able to identify for the unit test. Okay, so we're still talking about levers, but there's now something that we're going to learn about called the law of the lever. And you guys did a small activity, hopefully, where you got to see what it takes to balance a lever, A, by itself, but B, by adding different loads to the ends and at certain distances away from the fulcrum. And so for any lever, there are actually 2 torques acting on it, the effort torque and the load torque, which is what we just went through on each of those diagrams. Note that when discussing levers, the distance from the force to the fulcrum is often referred to as the arm. So you're going to see that actually in some of your examples. If you see effort arm, load arm, that's just talking about the distance you are away from the fulcrum point. Okay, so if we look at an example, these elephants would be able to balance this seesaw. So picture this scenario in real life, and these elephants are trying to balance the seesaw so that it's horizontal, just like you guys did in your activity with resting some sort of lever on your hand and trying to get it to balance horizontally. If we were to look at this same example with elephants, we have a heavier elephant on this end, so let's just call this the load force, because he's weighing this side down right now, and the object of this is to get this this lever balanced horizontally. What might we need to do? If this is our effort force, in this case it's down to get it balanced, we would need to balance the seesaw if they can make a clockwise torque equal to the counterclockwise torque. So they want to balance this movement with this movement so that it's completely horizontal. So we want it to look like this. So 2 things, we could either add more weight to this side, or as you probably determined in that activity, if this elephant here just moved closer to the fulcrum, so away from the end of the board, it's going to actually lessen the amount of load force, because remember, the further you are away from the fulcrum, the more force you end up having. If this elephant moves in this direction toward the fulcrum, then he's actually taking away some of that load force that exists from his weight alone. And then what would happen is it would end up balancing out till you end up completely horizontal. Okay, so when it is balanced, here's the different variables we have to work with. And I want you to start thinking about this when you see diagrams. So here's a first class lever. We have the fulcrum in the middle, effort force on one side, load force on the other. And what the law of the lever states is when we have things balanced, if a lever is balanced, then the torque on one side of the fulcrum is equal to the torque on the other side of the fulcrum. And recall that, so effort force and effort distance are on one side of the fulcrum. Load distance and load force are on the other side. So equally or separately, let's say, we could calculate the amount of torque on this side, and we could calculate the amount of torque on this side depending on these 2 variables, right? It would be 2 separate calculations. And all we need in order to calculate torque, recall, is torque equals force times distance, which is the note that we just covered. The only additional thing we've done here is we've applied it to either the effort side, which we call the effort torque, or the load side, which is the load torque. So it's this exact same calculation you guys just did, but it's now just separating it into what's our effort force and what's our load force. And when we talk about the law of the lever, basically all we're saying is that when it's balanced, if this is completely horizontal, then these 2 values have to be equal to each other. The torque, so if we have a balanced lever, then the load torque, so torque of the load, has to be equal to the torque of the effort if we have a balanced situation. So if balanced, then this must be true. These 2 sides must be equal to each other. Then load torque is equal to effort torque. And so what we're going to see is if we have a problem where it tells us that something's balanced, we can use this relationship. Because if we know that the torque on the load side has to be equal to the torque on the effort side, and we know how to calculate these individually, which is really just the force of the load times the distance that the load is away from the fulcrum, and the torque of the effort is basically just the force of the effort and the distance that effort force is away from the fulcrum. So this is a new formula that comes up just as a result of if we know something's balanced, then this must be true. So we're going to look at an example. And this is called the law of the lever. So when a lever is in equilibrium, so this is a fancy word for balanced. If something's in equilibrium, it means it's balanced, same on either side, okay? Then the effort torque is equal to the load torque, and that's basically what I just showed you. That effort torque is equal to load torque. And if we were to break this down, we know how to calculate torque is just force times distance. And all we're doing is separating it into effort versus load. Okay, so let's look at an example of where that is applied. So our example is a wheelbarrow is loaded with 140 kilograms of bricks. The distance between the load and the fulcrum is 0.5 meters. If the distance between the effort and the fulcrum is 1.5, what is the effort required to lift the load? This is a lot coming at us at once, so you might want to reread your statements a couple times and try to label things as you go through. Remember, they're going to either fall under the effort side of things or the load side of things. So as you go, maybe just pick a color. So a wheelbarrow is loaded with this many kilograms of bricks. Remember, your load is always the load side of things. So if we know the mass, so this is the mass of the load. And remember from our last unit that the force on any mass, the force of gravity on any mass, is just equal to the mass in kilograms times 9.8, or the acceleration due to gravity. So that's how we can figure out what the load force is. So we know the load of the wheelbarrow is loaded with bricks. They only give us the mass, but how do we figure out force? We multiply it by 9.8. And then we end up with what the load force is. The distance between the load, so we're still talking about the load side of things, is 0.5. So we know this must be the distance for the load. Now I'm going to switch colors because we're going to end up talking about the effort. If the distance between the effort, so this would be us lifting the wheelbarrow, so effort is in blue, is 1.5 meters, then what they've given us is the distance of the effort in relation to the fulcrum. And what they want us to calculate, what we don't know, is what is the effort required to lift that load. So what force is required for us to lift that wheelbarrow? So effort, force, is what we're trying to find. And I'm sorry, we've been using a capital E from the beginning, so let's keep that consistent. So what we're trying to find is the effort force. Okay, so first thing I recommend doing is what we just did here. Write things down as you read through the problem and try and identify what they're giving you, because when you have to write down your given information, it makes it a whole lot easier. So they gave us the mass of the load, but I told you, remember, if you have the mass of anything, the force of gravity on that mass is just that number in kilograms times 9.8. So we can figure that out from here. Actually, they're going to go through this, so we'll just leave that. And what other information do we have? We have the load distance and we have the effort distance. So we've just discovered those and written down what those are there. What we're trying to find is the effort force. And in order to solve this, like I said up above, we need to figure out what that load force is by figuring out what the force of gravity is on it. So remember, the weight of a load, if they just give you kilograms, you're multiplying it by 9.8 to get what that load force is. And that's all that's happening here. We have our 140 kilograms of rocks times 9.8. This tells us the force of gravity on that, which is also equal to the load force, always. Okay, so that's what we just figured out there. Let's get rid of that screen. So now we can proceed with the appropriate form of the law of the lever. So in order for this to be balanced, we're using this formula, and I'm going to rewrite it so that we can start times the effort distance equals the load force times the load distance. Okay, and what we have is we have 3 out of the 4. We'll always be going to be given 3 out of the 4 variables here, and you're always going to have to solve for that final one. So I want to show you what that looks like. Remember I told you the magic triangle for formulas only works if we have 3 variables, and you can see in this case we have 4 variables, so I can't give you a magic triangle. I can only show you how you do it. And the best thing you can do is at this stage substitute all the numbers that you have in. Okay, so our effort force is what we're solving for. This is the one we're solving for. We don't have a value for it. But we do have our other 3, and they're right here. So our effort distance is 1.5. So we can put that in. So it's still our effort